Good morning, everybody. Welcome to this contest. I think it's pronounced AIsing, but that might be AIsing. I'm not really sure if it's a capital I or an L. As far as I know, I think this is pretty much the same as an AtCoder beginner contest. That's the mindset I'm going into it with. Hopefully the problem should be pretty easy, but we'll see. Good luck, have fun to everybody competing, and I'll see you on the scoreboard. How many multiples of D are there among integers from L to R? So it looks like just the naive is fine. Just one test case too even. Count all of them and then print the answer. I think it's inclusive, but we'll see. How many multiples? Got it. Yeah, okay, so I solved the wrong problem here, but C plus equals R over D, C minus equals L minus 1 over D. All right, there you go. Oh, we have to call this main, and then we're good to submit. Cool. An odd problem. We have n squares assigned the numbers 1 to n. Each square has an integer written on it, and the ith square has this integer. How many squares satisfy both conditions? The number assigned to it is odd. The written integer is odd. Man, that is a boring problem. Okay. We've got our array for int I equals 0, I is less than n, I plus equals 2, if a at I mod 2 equals 1, and increment our counter, and then print the counter. I started 0 because I'm assuming that their stuff is 1 indexed. Alright, problem C, x, y, z triples. Let this be the number of triples of integers that satisfy both of the following conditions. They're all positive, and the cubes of each of them plus the products of each of them is equal to n. Given an integer, n, find each, wait, what? I see. Yeah, okay. Okay. Does this end up simplifying somehow? It looks like the kind of thing that does. Well, alright, so none of the integers can be bigger than 100, right? Because if any is bigger than 100, then this is already too big. So we can just do the n cubed and count. Yeah, okay. For each integer from 1 to n. Okay, so n plus 1. And now for int a equals a is less than, or they each have to be 1 equals 1, a is less than 101, we have each of these, and now int val equals a times a plus b times b plus c times c plus a times b plus a times c plus b times c. Okay, is that going to overflow? No, it shouldn't. If val is greater than n, continue, and if val plus plus. Yeah, looks fine to me. All right. Hope your day is going well. I've only mindlessly run through these problems. Let pop count n be the number of ones in the binary representation of n. For example, pop count 3 is 2, pop count 7 is 3, pop count 0 is 0. Let this be the number of times the following operation will be done when we repeat it until n becomes 0. Replace n with n mod pop count. You're given an integer x with n digits in binary. For each integer I up to n, let this be what x becomes when the ith bit is inverted. What? Oh, okay. So we have so we're going to invert each bit and then count how many times it takes to become 0. This suddenly got like a lot harder. So we can pre-comp all of the answers for all n less than 2 times 10 to the 5th. And that'll be at most how big it is after each step. Then we would need to know the value of this thing under mod of both the number of ones it has and the number of ones it has -1 and the number of ones it has +1. I think really we don't care about the number of ones it currently has. We just care about -1 and +1 because it's going to change for sure. So yeah, I don't know. I feel like this is not a difficult problem, but it seems okay. Makes sense. So that is, in fact, what the scoreboard would suggest as well. Let's read E in case. We have n camels numbered 1 to n. Snook has decided to line them up in a row. The happiness of this camel will be L if it is among the k frontmost camels or R otherwise. Okay. He wants to maximize the total happiness of all camels. Find the maximum total happiness of the camel. Why is this not trivial? I'm very confused. Why is this just not 2 multiplications and an addition? I must not understand the problem if this is harder than D. Oh, they have different requirements, I see. They're different for each camel. Like each camel might want to be in a different position. Yeah. All right. Cool. So we understand that problem. Let's read this, then we can go back and actually solve some things. For each integer n, he will choose integers s1, s2, n1, n2, u1, u2, k1, k2, e1, and e2. Okay. And the sum of them is less than n. I see. So we want to find 5 pairs of integers with like several of these constraints. And then multiply all of their ranges. This seems tricky. Yeah, this is a really steep difficulty curve here. Like banger, banger, very easy, medium, and then these are non-obvious. 1, 1, 1. I suppose we should read E. So I'm getting a really all that matters, this is our range. All that matters is the cutoff point and the difference in values. Like if we're gonna get 10 points either way, we might as well look at this cutoff point. Oh, and Ri, can Ri be bigger? Yeah, Ri can be bigger, that's annoying. Well, maybe it's not that annoying. It might not matter, it might just be a negative difference. So initially, we'll process things in order of this. Yeah, so we have n different events, and then each one has some delta. And we also have like some number of spots left over. So when we hit somebody, we'll put them in some spot. And then if we hit somebody else, we will put them in a spot if we can. Now if we hit somebody else and we can't put them in a spot, then we can leave them out to die in the later half of the array. Or alternatively, we could swap them with someone we already have. We would want to swap them with the person with the smallest delta. And I think that's fine. Yeah, that should be a fine approach. Okay, so we know how to do D and E. We don't know how to do F yet. But to be honest, F seems very math heavy. And I think there's a very real chance I just am not able to solve it. So from a scoreboard perspective, I think solving E and solving D are the right moves in this situation. Okay, so we'll make a camel, and they have a split point, right? Int and then int delta, or int difference, I guess. Cool, so we have these camels. Now we need to make them. We're given KLR. Okay. So camels at I is new camel. The split point will be K, and the difference will be R minus L, or L minus R. Yeah, okay, and now int equals 0, int plus equals R. Good. So now at the end we can print answer plus like some best probably. So now we need to sort the camels by their split point. Okay, so now we need to walk through each of the camels, or maybe just walk through each of the positions. I think it's probably easier to walk through each of the camels. But I might be wrong, we might end up changing this later. So now int d positions equals c dot split point minus position. Okay, so what else do we need to keep track of? Int the number of spaces. We also need a priority queue of removable things. Okay, so now that seems fine. So now when we have a camel, we can add a bunch of spaces. Plus equals 2 positions. So now we have all of these extra positions left over. So now if n spaces is greater than 0, then we'll just add this camel anyway. Otherwise, if it's 0, that means we have like too many camels for our own good. What a funny sentence. Then I think we can just remove from this priority queue and replace it with the best camel. Or maybe we don't. Yeah. So if removable deltas dot peak, if this is less than c dot difference, otherwise we just remove this current camel. For int I and removable deltas, then ans plus equals I. All right, let's see. What does this look like? All zeros. That is, I guess, not a good sign. Is this the first test case? What's the first test case? 2, 3, and then 19. Okay, so this is test case 1. This should definitely not be 0. This should be pretty easy to figure out, I think. Maybe I was running the wrong problem. The answer is 25 even. So if this is within the first 1 camels, it will be 5, otherwise it's 10. If this is within the first 2 camels, oh, these need to be -1. Initially it is 15. No, it's not. It shouldn't be. Yeah, it should be. So we've got an extra space. Okay, then we just need to see this out. So we're considering the thing at position 0, the delta is -5. Yeah, this isn't necessarily good. So maybe this approach is just wrong. This isn't necessarily good because you don't necessarily want to be in the front. back to the whiteboard. So we've got some range. And then we'll have a bunch of elements taken. So we've got some range, and we have a bunch of preferences of different importances. So we might want to be like, yeah, we can process all of the leftward ones. And we can give process all of the leftward ones and then give precedence to as many as we would like, and then do the same thing in the reverse direction. And they shouldn't overlap, because any constraint for the ones that want to be on the left side, if they don't get what they want, they can just fill in the gaps at the end. And if they do get what they want, they won't interfere with the people who want to be on the right side, because those are just like, they want the exact opposite thing. So they should be able to coordinate. Like they have aligned goals, basically. They each want to be on the same side, or like they want to be on opposite sides of each other, so they should agree. So there would be no conflict. Yeah, okay. And that should be right, I think. So what do I need to do in order to make that solution match this solution? So if L is less than or equal to R, then go left.add new camel from, what's its position? So its split point will be K, and then it will receive L minus R. Otherwise, go right.add new camel, and then I'm going to make this 0 indexed as well, so its position will really be n minus 1 minus k, and look at R minus L. Let's make a method for this. Okay, so now ans plus equals solve go left, ans plus equals solve go right. All right, so now we just need this method. So we have this last position, the number of spaces, this removable deltas. Yeah, so now everything wants to go left. So this should be easy. So how many positions we have? We add this to our number of spaces. We also need to sort this. Why is that? If L is less than or equal to R, it should be greater than or equal to R. Then you want to go left. 25. Which makes sense because 10 was the smallest you could do. All right, so let's see. Are we right, or do these samples get more interesting? Uh-oh. Uh-oh. We have a problem. That's very bad. 260? No. So we are somehow doing too good. Which I think would make sense because we're assuming that these things do not intersect at all. But also that should be true. Well, on the bright side, we have this very nice test case that should break it for us. What does this look like? We have 3 positions. Then when this is going to be, okay, so this one, how do we draw this like this? So this is going to be 93, 78. Then, nope, that's 2. One 71.59, and then this one is going to be 57 always. I think I'm handling that wrong then. If this is n minus 1. If k, so in this case, k is equal to n minus 1. So really it should be n minus k. So if removable deltas dot is empty, then we just can't have it. This is n minus k minus 1. This is k plus 1. So k was 3, n minus 3 is 0. Why? What is going on here? Okay, this is some sketchy math, but it passes sample, so I think I'm going to submit. How many test cases are there? I've done a bunch. Okay, it looks good. Ooh. Wrong answer, huh? Probably all wrong answer because it's multi-test case. Well, we'll come back. How about that? So for this problem, for D, we need, should be pretty straightforward, I think. So we're going to need a couple things. We need to store the value modulo 1 bits plus 1. And we also need the value modulo 1 bits minus 1. Assuming 1 bits isn't 0. Yeah, but just be careful there. Now if we change some number, the value will change in some predictable way. And then we can also just calculate the answer for everything that's relatively small. Yeah, okay, good. We already have a, yeah. Okay, single test case. So what are we going to need? We're going to need probably the 2 powers pre-computed. Well, let's just do our mod stuff. Do we need division? No, I think we just need addition, subtraction, and possibly multiplication. addition, subtraction, multiplication. Good. So int bit count equals 0 for if this is a 1, then bit count is plus. Okay, so now we need these two powers. Yeah, okay, and then also static long, stat small. So this is going to be 1 plus steps small at I mod I, or integer dot bit count of I. Yeah, okay, so that should be fine. Or this should be 0 actually. Good. Now, okay, so now M1 or mod equals bit count minus 1. Now 2. Oh, okay. If wait. Yeah. So we only want to do this if bit count is greater than 0. Then 2 pow m1 equals, or at 0 equals 1. From I equals 1. Then it's 2 times the previous thing. I didn't make these static. What a fool. Okay, good. So now we have this. So that should be all of the pre-computation we need. So now, what do we need to do? We need to print each answer. So what is the first bit? Is the first bit, when they give us this 0 first, is this the most significant or least significant bit? So 1 equals 7. So it looks like this is the least significant bit. This is 2 to the 0, I think. x2 equals 1. Wait, what is? Oh wait, no, this is most significant. Okay. All right. We also need the value under mod. Yeah. add this to C minus 0. Okay, so now we can maintain this. Now mod equals bit count plus 1. Multiply val2 by 2. Okay, so now we have the two values under mod. So now we need to print the answer for flipping each bit. So int power is going to be equal to n minus 1 minus I. And then if this is going to be, so if line at I is a 0, then we do one thing, otherwise we do the other. So if it's a 0, we turn it into a 1. So now we care about M2, because there will be one more 1. So then we want this to pow power. Oh, to pow M2 of power. Now system.out.println. The small thing, what did I call that? Steps small at int new val. Good, okay. So now if it's a 1, they count minus 1. So if mod is equal to 0, that means everything is a 0, so then system.out.println 0. Otherwise, then we care about stuff under mod of M1, and really we want to subtract this thing at this power, and now we want that step small. Okay, I think that's fine. All right, so do I need to add 1 because this is under mod? Huh. I think I do. I think that needs to be plus 1. And now if it's 0 under mod, like if this is 0, if the mod is 0, then the answer is just 0. If the mod isn't 0, then I add 1 here. Okay, the classic test case. Good thing we tested it. bit count, or this should be mod. Mod is greater than 0. Good. So maybe this is harder than an ABC. Like, no one's even solved it yet, so that indicates that it is harder than an ABC. Let's do E. Let's fix E. Yeah, so that was, I'm happy with that solution. E and F are what's left. And like looking from standings, it looks like E is an order of magnitude easier. And also like from just subjectively, I'm very bad at math problems, and F is definitely a math problem. So E is where I need to be at the moment in terms of placing well. Although like that's already going to be sketchy, but we'll see. So we've got a bunch of camels. And then, yeah, you've got a bunch of split points. You've got one thing on the left, one thing on the right. So what is my solution currently doing? We've got a bunch of camels that want to go left and a bunch that want to go right. We have this split point. So this is going to be equal to, for in the first K, then we're good. This is what I don't believe this. This seems very sketchy. Well, no, that's fine. I think that's actually fine. Because this is just how many spots there are. That's like the index of the last spot. And then this is the index that, yeah. So this is like the index of the last index of the left, plus 1 will be the first index of the right. So this math should be legit, I think. So now I solve for both of these independently, then print out the answer. Yeah, that should be fine. So the last position that I've seen is -1. Initially, I have 0 spaces available. Then I look at each camel. I get this many. Oh no. Oh, am I silly? Well, this is a problem. That's a bug. How does that pass? I guess samples are just really weak. Okay. Well, we can break that. Or let's say these are both at position 1. Okay. There you go. So they can't both be there. Now we've got one at position 2, 0, 0, 3, 0, 0. Or I guess let's make it. So now the answer here should be like 102. Wait, what? What is going on? Extra. How does this have no room? D position should be. How is it 0? Oh, that's because I have this. Did I not have this earlier? Yeah, okay. Can I see my submissions, please? How do I... I should know how to use this website. Last time I asked if you could do, like, friends. Oh, results, my submissions. Here you go. Yeah, okay. So that's the bug. Now it's fixed. All right. Looks like that was it. Good problem, I enjoyed it. So now we're left with the math. Yeah, now we just gotta do this math. All right, so how does this work? You've got man, this is 5 things, huh? That's a lot of things. So we pick 10 numbers. I guess I can solve this in end of the 10th. Is that good enough? Is this just pattern finding? Do I just write out the brute forcer and look for patterns? I don't even know where to start on this problem, to be honest. Like, it seems like they're looking for some sort of end of the 2/3 Mobius inversion or something crazy. Yeah, well, the next 40 minutes are just going to be me mindlessly trying to come up with math solutions to this. Unless maybe, I think this is going to be a polynomial. What if this is a 6-degree polynomial or 10-degree polynomial? Wait a minute. If it is, that is epic. That means I solved a math problem. So if you're picking one thing, how many ways are there to do that? I guess there's one. What if you're picking two things? You can pick 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. Equal to like what, n times n minus 1 or n plus 1, I guess, over 2. This turns into n squared. They give you really good samples for this. They do give you pretty good samples. Well, that's one idea. Maybe it is just a polynomial that we need to find. So surely we want a brute forcer for this problem, right? There's no way we don't. right, so yeah, okay. Essentially, there are 10 numbers, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or I guess number of pairs would be better. Well, I guess just while true. There you go. That's how we start every sentence. Do this forever until I tell you to stop. So now a at 0 plus plus. Or wait, what did they say? They say the sum is less than 9. So a at 0 plus plus. If a at 0 is greater than a at 1, then a at 1 plus plus. Okay, now if a at index plus 1 is greater than n, the next thing is bigger than n, then a at index plus 1 oh wait, what do we do here? Then we set ourselves to 0. A at index equals 0. Yeah, so if this next one is bigger than n, then this next one equals 0. And a, well then index plus equals 2. What did I just do? Okay. So if index is greater than, well, if it equals n pairs, then return int. Needs to be times 2, then a at index plus plus. Yeah, okay. Else break, else break. So this will increment one thing. So now we just need to check if this is valid. Okay. So we know all of the pairwise things are fine. Now we just need to check the sum. And we need to add up the product. Yeah, okay, so how do we How do we look at the sum? The sum is going to be okay. Now we just need to add up the product. Okay, so I think this is fine. S1 is less than S2. Okay, so blah, 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 blah. Yeah, okay, so now if we reset this, we want to reset it to 1. And now all of these should be somewhat valid. Okay. Okay, so lots of stuff happens. That's not important. We care about when the sum is small enough. Which happens these times, these 5 times, right? There are 5 times. There are 6 times. Uh-oh. Oh, I'm missing the original. I guess we could make the answer 1. That would handle it. Oh, wait, no, we can't make the answer 1 because it's not always 1. well, oh, that would do it. Ans plus equals this index, this array, this number of pairs. Okay, I see. And then what else? Ans equals process for value, that n, that array, these pairs. And then it just needs to be a long. Should also be long. $352. Seems unlikely. Yeah, not 352. But also, these numbers should not be showing up. So that means we're getting the sum wrong. The sum is greater than n. What is n? N is 6. That is 7 is bigger than 6. Hello. Ah, yep, that should be n. We're still wrong. How are we still wrong? Oh my goodness. Should be 1 plus 2 plus 2 plus 2 plus 2 plus 2. Am I just like stupid or something? What? Prod equals multiply the product by that thing. Okay, fine, finally. So now if we do this with 10, we get some number that is right. Okay, so how much time do we have left? We have 19 minutes. So I think the play is, if instead of having us do this with 5 pairs, we just do it with 2 pairs. Then let's see if this is a polynomial. So when n is 2, we get 1. 2 is probably uninteresting. Well, maybe it's not. Two, 1, 3, 5, 4, 17, 5, 45. What degree do we think it is? 6, 103. Come on, Give me my polynomial, please. Not helpful. Okay, let's write it ourselves. So, yeah, okay, so 4 into I equals 4 I is less than, or I equals, what does I have to be at a minimum? Equals 2, I is less than 5, I plus plus. Wait, what? I plus solve I. That's what we want. So here are our points, okay? So now we need a polynomial finder. And what is this gonna read? So we will probably read n into array poly. Okay, so how do we actually do this? It's been a while, I forget. So we've got some ax0 or what is it? It's going to be ax to the 0 plus bx to the 1 plus c x squared plus dx to the third. So f of 0 is going to be equal to a. Yeah, now f of 1 is going to be equal to, well, so then we can subtract out a. From everything. And then once we've done that, divide by x. Yeah, I think that works. So we want to read in each of these. Okay, so now x is at 0. It's going to be equal to, oh, we need our answer here. So ants at 0, or ants at I, equals x's at I. For in j equals I plus 1, j is an j plus plus. Y's at j minus equals ants at I. subtract out this thing we found, and y is at j also divided by equals x. Because it has an extra factor of x that we don't actually want it to have. So let's do a test case. So let's say our polynomial y equals x squared minus 3x plus 5 plus 7, I guess. So 0, 7, 1, be 1 minus 3 plus 7, which is going to be equal to 5, right? 1 minus 3 is negative 2 plus 7 is 5, okay? And 2, 4, negative 6 plus 7, which is also equal to 5. Okay, so the format is going to be the polynomial of degree, let's do degree 4 actually, just see what happens. So at 3, this would be 9, negative 9, positive 7. So 4, oh wait, divided by equals this isn't right. So this should be x is by, no, this should be, this isn't, oh my goodness, what am I doing? This y is going to be equal to this, or this value is going to be equal to this y divided by math.pal x's at I write our own power function. Okay, so this y divided by, we have 10 minutes left. Okay, divided by this x to the ith power. So now for each future thing, subtract out this answer times x's at j to the times, wait, subtract out, yeah, this thing what am I doing? How do you do this? You first you can find a by evaluating it at x equals 0. Man, this is just like inverse f of t. Come on. F of 0 is equal to a. So now we have this evaluated at several points. So now we have b1 bx1 plus cx2 plus dx3. Yeah, we divide all the y's by x's now. So this is going to be y's at I. Now we need to subtract out this from every future thing. So all future y's minus equals this answer. And also y's at j divided by equals x's at j. Okay. So there are, this x is not actually a thing. There are 4 points. There is 0, 7, 1, 5, 2, 5, and 3, 7. This first polynomial should definitely be a 7. Right? Oh, it's because I'm reading these in the wrong order. Yeah. Seven. Not quite. So what happens? So we subtract out 7 from these. Now what do we have? We've got, or we subtract out 7 and divide. So we've got 1, 5 minus 7 divided by 1. Equals -2. Can you not just do that? Why does that not work? Need to divide each term by x. So we've just subtracted out, we had a plus bx1 plus dx2 plus dx3. We subtracted out this a. Now we have this. If we divide this by x, don't we get bx1 or b? We should get b plus c x1 plus dx squared. But I guess we don't. So what's the real example? x equals 7 plus negative, or 7 minus 3x plus 1x squared. So when x equals 1, we have 7 minus 3 times 1 plus 1 is equal to 11. Not equal to 11. It's equal to 5. So if we subtract out 7, we get negative 2 equals this. Oh, yeah, because we're not evaluating it at 0 anymore. Now we're evaluating it at 1. Yeah, I guess I don't know. Unfortunate. Well, alright, so I guess let's go over solutions. So, cool, problem A. So problem A, I guess, is pretty boring. It's really just implementation tests. So you have to check how many integers are there in the range L to R that are multiples of D. So if you, like, let's say D equals 4, then then if D equals 4, then you have like non-multiple, 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 and then your multiple, then non-multiple, 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 your multiple. So what you can do is you can, like, if you have some integer x, so this is like the prefix you're looking at, if you have x divided by D floored, that's going to be how many circles there are in this range here. So if we want to see how many circles are in some LR range, we can take L minus 1 over D, I guess, floor that. And then we can also take R over D, floor that. So this will be your final answer. This is like the number, so if you've got like some range here, this is the range you're interested in, you want to see how many are there less than or equal to this part right here, and then also how many are there less than this that you overcounted. So you subtract out those, then you're good to go. Awesome, so that's problem A. Let's move on to problem B. So in problem B, you have a bunch of squares. You want to see how many squares are both odd and have an odd number written on them. So you just check all odd positions, count how many of those are odd, and that's it. Yeah, I don't know. That's it. That's it. Just like check the odd positions in the array, see if they're odd. In this example, or in this problem, you want to see, what's it saying? How many triples are there? Yeah, okay. So you want to see how many things are there where this equals x for some value. The thing to notice is that you square each of these terms. So if you have any term that's 101 or bigger, then 101 squared will be bigger than 100 squared, which is 10 to the 4. So that means each of these values have to be between 1 and 100. So you can just check all pairs of those. There will be 100 cubed total pairs, so 100 x choices, 100 y choices, 100 z choices. Those are independent, so you can multiply them. So there are 10 to the 6 total choices. Just evaluate each of those and then store what value they're equal to. Now at the end you can go look up what they look like. Here's the code for that. Just like try all pairs and then put it in your array somewhere. Cool. Problem D rather. Anything goes to 0. So yeah, so if you what you can do for D is if you've got like some number, maybe it's like, I guess 7 is a good example. So this is equal to 7, this in binary is equal to 7. Then you take this mod 3 because there are 3 1-bits in this number. So that would be, this is equal to 1. And now 1 in binary is just as 1 1-bit, so 1 mod 1 is equal to 0. So you do 2, oops. You do 2 of these, man, what am I doing? 2 of these modulo operations, and that's what's interesting. So, yeah, how do you do this? So if the values are small, like if they're less than or equal to 10 to the 5th maybe, if the values are, not the number of digits, then you could just do it naively. You could do like a DP. So DP at I would be number of steps it takes for I to get to 0. And then this is just like equal to 1 plus DP at I modulo number of 1-bits. I think they called that pop count at I, or of I. So that's your DP, really easy to write, but you can't do that because n might be huge. So what we're going to do is the first step we're going to do in a smart way, and then after that we'll pre-comp the answers for all smaller steps. So yeah, how do we do this first step? So if you have some really big number in binary, like maybe that's your number, if you change one of the bits, the total number of 1-bits that are going to be in that number will either be equal to the total number of bits that are there now plus 1 or minus 1. Like you either turn a 0 to a 1, in which case you add a 1-bit, or you turn a 1 to a 0, in which case you decrease a 1-bit. So what we're going to do is we're going to be modding this value by the number of 1-bits that it ends up having. So what we need to do is we need to know what will the new value be under the mod of however many 1-bits it's going to have. So we can calculate this value under 2 mods. So we'll calculate it, in this case this has 5 1-bits, right? We'll calculate this value mod 4, and also this value mod 6. And then if we change this 1-bit, or this 0 to a 1, we can see what is 2 to this power. So this would be like 2 to the 0, this is 2 to the 1, 2 squared, 2 cubed, 2 to the 4, 2 to the 5. So we can see what is 2 to the 5 under mod of 4 and under mod of 6. And since we, I guess in this case, we'll be using the mod of 6, because there are now 6 1-bits here, we want to see what was the old number's value. So it was the old value mod 6, plus we've also added this extra power of 2. So the old value plus whatever 2 to the 5 is mod 6. That'll be this new value, mod 6. The number of 1-bits here is going to be less than or equal to like 10 to the 5th or whatever, like 3 times 10 to the 5th. So we can pre-comp the answer for that. And then we can see, once we know its value under mod, we have those all stored in some table, and we can just like print that answer from the table. So we can do this in order max value, or order number of bits, I guess. It's like ordered 3 times 10 to the 5th, so that should be fine. So just to recap quickly, because it's kind of lots of parts of the solution, we know we just want to calculate the value of this number under mod of the number of 1-bits it has plus 1 and minus 1. And then when we have one of these bits that we want to swap, we know how that will change the value under mod, and we also know what mod we want to look at. And then once we have the value of this number under mod after the first step, it will get small enough that we can just store all of those answers in a table. We just use our lookup table. Cool, so that is problem D. Problem E was also quite a cool problem, I thought. Camel train. So in this problem, you have a bunch of camels. And here's my picture from it. But basically, you've got a bunch of camels, and each camel is like, well, I don't know why they're camels, really. Maybe it's just like an AtCoder theme that I'm not familiar with yet. But this camel might be okay. If I'm in the first several positions, then I will get +5 points. But if I'm in the last several positions, I will be very happy. I'll get 100 points. Maybe you have some other camel like this. This camel gets 7 points if he's in the first positions, or 4 points if he's in the last positions. And you can have a bunch of different camels with different preferences of where they want to be and how happy they will be if they get in those positions. So in order to solve this, what we can do is first we want to put each, like we have really two different problems here. We have one group of camels that wants to be in the front, and we have one group of camels that wants to be in the back. And we have n positions and n camels as well. So we know, like, if you want to be as far forward as possible, then it doesn't, like, the camels that want to be in the back are never going to get in your way. Because if there's an extra spot, right, if you want to go forward, and you are, or if you want to go, yeah, if you want to go forward and you're here, and then there's some other camel back here, he wants to go backwards, you're never going to get in each other's way with your requirements. Because one, you could just like swap them, so there's that argument. And two, if you imagine these are like a herd of camels, right? Some camels want to go forward, some camels want to go backward. They all have the same interest. They're working toward a common goal. They want to switch positions. Like they want to both move to the, like they prefer the same things. So they're not going to get in each other's way. So basically, the only camels that will get in each other's way are if you have a bunch of camels that all want to move toward the front of the pack. So maybe you've got like all of these camels here, and they all want to go forward. And it's possible there aren't enough spaces to fit all of the camels that you want. So to do that, we can do a combination of like a, really it's just a greedy. We can like look at, so we've got, now we have just the simplified problem that we're going to do twice, where we have a bunch of camels that all want to go to the front. So we can look at the camels in increasing order of their cutoff point that they want to be in front of. And if we do that, what we can notice is that in some prefix, we want to take as many camels as we can. But in addition to doing that, of the camels we can take, we just want to take the most valuable ones. And then we'll throw out the ones we can't use. So here, if we have one space, we'll take this one camel. And then, so now we have this one camel in our stash, and we have 0 extra spaces. Now we consider these two camels, and we want to take the best of them. So we want to take whichever one is more valuable, and then the less valuable one just won't get a spot. Now we have this extra spot here, so we'll save up that spot later. And now we have two camels here. So this first one we can just fit in that spot, right? So now this one we'll get for free. And now this one here can fit in this spot here. So that works. And now maybe we have like 3 camels here. So the first camel can fit in his spot, but now we have these other 2 camels that need to fit in this range, and there aren't any more spots for them. So what we want to do is we just want to find the smallest camel in this range to remove, the least happy camel, right? The one that matters the least. And we can remove him and replace him with this one, if that's beneficial for us. So yeah, when I say like the least happy one, what I mean is there are some camels that are naturally happy no matter where they are, and those camels we don't really care about, right? So if you get 100 happiness for being in the front or 99 happiness for being in the back, really like you're gonna get 99 happiness no matter what. So what we can do is replace this with just 1 happiness in the front and 0 in the back. So now all we care about is this non-zero number. So we want to find the smallest non-zero number, and then see if we replace this camel here with it. Maybe this is the guy we want to replace. Oops. So now the question is, if we replace this camel with this camel, is that a beneficial trade or is that a hindrance? And if it's beneficial, then we just pop this from our priority queue. We just use a priority queue and replace this one. And we keep doing that as long as it's beneficial. Eventually we'll run out of room, then we just throw out the unhelpful people. Okay, cool. So that is camels. You can do it with just a priority queue and some observations. Let's talk about this problem F. so I don't actually know how to do this. My suspicion is that this turns into a polynomial. I guess, is there a editorial out already? Doesn't look like it. So I think this problem turns into like a degree 10 maybe polynomial. And the way you could solve it, if you know it's a degree 10 polynomial, is you could evaluate it at 10 different points. And then once you've evaluated the polynomial at 10 points, 10 different ends, you can have 10 different points for that polynomial, 10 different xy pairs. So you've got the input x and the output y. And if you have that, you can figure out what the polynomial is. So that's one way of doing it, I guess. And then you can do all of your operations under mod here. I'm not sure that that's right. It might not be a polynomial. It might be... Well, I mean, I say it might be exponential, but I really don't think there's any chance it is exponential. I think it's definitely very small. Like, it's... If you double n, the answer is not going to increase by more than n to the 6th. Right? Like, it's... Or n to the 10th. Like, it's bounded by n to the 10th. It's not exponential. I don't see any reason why there would be logs, so I'm pretty sure this is some polynomial. You just need some code that can convert 10 points or something to 10 different values. And then you do that under mod. So that's what I was trying to do in contest. I didn't have time to finish coding it up, but that's like a pretty common idea. I won't explain exactly how to do it, but the general idea is like if you have some quadratic function, if you're given 3 points on that quadratic function, maybe like these 3, there's only, as long as you know it's quadratic, there's only one function this can be. And similarly, if you're given some line, if you're given 2 points on the line, there's obviously only one line that goes through those 2 points. So you can figure out what that line is. You can figure out what this parabola is. If you have like some cubic function and you're given 4 points on it, so maybe you're given this one here, this one here, this one here, and this one here, then there's only one cubic function that goes through all of those. Yeah, so I don't know the math in order to be able to explain that well, so I won't try. But I'm sure there's a good way of doing it. And then if you're able to convert backwards from that, I think you can just come up, like write the brute force, come up with the first bunch of these, and then once you have, like, come up with the first like 10 points or 11 points maybe. Once you have the first 11 points, you can like find what the polynomial is. And then you can just like hardcode the polynomial and submit it for this massive case. And you're also given this huge number, right? So if you have this huge number, then you should be able to test it. Like if you pass this test case, there's no way you're going to be wrong. So there you go. All right, so yeah, those are solutions to this contest. Hope you enjoyed the contest. Hope your rating went up if it was rated for you. I don't know, maybe it was rated for me. I'm not really sure. Let's see, is there a rating boost yet? Not yet. It is rated for me though, because I'm under 2,000, so we'll see. I'll see you in the Code Forces round. Starts in about an hour, I think. I might take a quick nap. Get ready for that. But yeah, good luck, have fun. Hope you enjoyed. Goodbye.